Let's start a discussion with vector calculus. Vector calculus is very useful in fluid mechanics. It helps us to identify how the flows move from point A to point B. To do that, before we do anything else, let's do a few let's give some definitions here. The first definition is what happens when we differentiate a vector. Differentiation of a vector. Okay, so let's consider a vector of the following form. Let's suppose I have a vector A. Okay, this vector A is a function of the magnitude A, and it's in the direction, unit direction, et. Let's suppose they're both functions of time. So that means that if I want to take the differentiation of A respect to t, using the chain rule, this will be the derivative of A respect to t times the second term plus A times derivative of E respect to time. Okay, this term right here represents the change in magnitude. This represents change in direction. Okay, so basically each one of these terms have their own representation, right? Okay, let's suppose we have various cases. Just for sake of this exercise, let's say your vector A is a function of time, and you have another vector B that's a function of time. You have vector B is a function of time. You have vector C that's a function of time as well. Let's suppose you have another vector U that's also, this is just a constant, and it's a function of time. Okay, so we have this definition. So if I wanted to do the derivative, let's say, of U times A, remember this is a scalar, it's a function of time, just a scalar. So if I use the chain rule, this is du dt times A plus U dA dt. However, since this is a scalar, but it is a function of time, so this remains there. If it was not a function of time, then this term would go to 0. If I was going to take the derivative of time of a dot product, let's say dot product of A with dot product of B, then it applies the same rule. It's a dot product of A respect to time times dot B plus A, don't forget the dot, there's a dot product there, then the dot product of B respect to time. If I'm going to do the cross product works same. Cross product is if you have A and you want to take the cross product with A respect to B, then that would be the derivative of the vector A cross product B plus A cross product the derivative of B respect to time. Okay, so many of these chain rules apply as we are used to applying them. Okay, so these terms becomes very useful and very handy as we are moving on, right? So another thing that's very useful to understand if I have the vector A, now let's express the full vector A that's a function of time. And let's say this is a function of A1, E1. Everything is a function of time. E2, E2, A3, E3. And I want to take the derivative of A with respect to time. That would give me the derivative of A1 respect to time, E1 plus derivative of times A, this is a vector, don't forget, no, this is a scalar, sorry. A1 times derivative of E1 respect to time. Note that if these were not functions of time, that this term will go to 0, okay? So going to the next term, that will be this term, will be plus dA2 respect to time, E2, plus A2 D2 respect to time, okay? So if you go to the last term, becomes then plus derivative of A3 respect to time, E3, plus A3 derivative of E3 respect to time. So this is what your differentiation will look like. This is a quick review of your calculus but in a vectorial notation. Okay, so the couple more, if you're working in cylindrical coordinates, that becomes very useful, and we use this a lot because the fluids are many times circular, and cylindrical approximation and spherical approximation become very handy. So the cylindrical coordinates tell me the following, okay? So let's suppose I have a vector, and this vector, the small variation of this vector respect to time, respect to position, is given by the following: r d theta, theta, plus d theta, d theta times z. Okay, dz times z. Okay, so now let's take a position vector and okay, so I have y, I have x, and now I'm looking from top, and I have a rotation that looks something like this. Okay, it's a perfect circle. And now I got a position here at theta, okay, but then I have another position here at another moment that it is d theta. Okay, so we know that both are r, but this is the same radius. The radius doesn't change. And this direction, let's change the colors here. So this direction coming in this direction is ER, okay? And we can call this, remember, just because the direction is going to change, the magnitude is still 1, let's put this prime. Then what you have is, you have a vector that here that's perpendicular to this at 90 degrees, have another vector that's perpendicular to this at 90 degrees. And this is the direction E theta. This is the direction E theta, but it's different because it's a different location. Okay? And we are doing all this rotation about this point, let's call it the point A. Point O, I'm sorry. So if I want to know the change between this the change that's happening here, the theta, okay, what is this guy over here? So what happens is you can show that delta E theta, okay, is going to equal to your final E theta, this vector minus this vector, minus prime minus E theta, okay? But that is nothing else than if you use your the rules of the arc, right? That says this distance is equal to r times theta. So, and it will be minus d theta er. So your d theta, if I'm actually going to take a very small differential, is equal to minus theta er. Okay, so what this is, this relationship is very useful, and also, and then in the same manner, you can show that dr er is also equal to d theta e theta. Okay, you can show that. I'm not going to go into the whole derivation here. You can also show that a differentiation of the E theta C will be theta, but since I can say EZ and take the cross product of EZ, it's the same vector, so that will give me equal to 0. Okay? So those are some concepts that just to tell you how it works. Now, let's consider the following case. Let's consider I have a velocity, okay? Now, this velocity is a function of x, y, z, and time. And I want to find the acceleration, okay? So let's suppose I want to find a small variation of this. A small variation of this is equal to using the chain rule will be variation of v respect to x d of x plus partial variation of v respect to y dy plus partial respect to v respect to z dz plus partial derivative respect to v respect to t dt. Okay, so pay close attention here now. So what happens here is we are doing this whole thing. I can divide this by t on both sides. So let's put this in a different color. So this is divided by dt. This is divided by dt, divided by dt, divided by dt, divided by dt, and note that dt over dt, this is going to be 1. So your entire equation then for your acceleration is actually equal to the variation, the partial derivative of v respect to t, okay, plus partial derivative of v v respect to x. What is that? That is nothing else than your component in u. Remember that the whole thing here, I can also write it in terms of ui plus vj plus wk. Okay? Well, these are the various components of x, y, and z, and they all can be a function of x, y, and z. So I can say this is this right here is nothing else than u. This is nothing else than v. This is nothing else. I'm sorry. Okay, they're related to this. This is nothing else than w. Then really what you're really having is u, velocity in respect to x, plus v, velocity respect to y, plus w, velocity respect to z. Okay? So this is what we call local derivative. This is called the local derivative. This is called the convective derivative. Okay, and a very convenient manner to write this is in terms of the gradient operator. So let's define what the gradient operator does. So there is the gradient operator. Okay, the gradient operator says your delta is equal to I times partial of x plus j, this is unit vector, partial of y plus k partial of z. Okay, this is what your vector is going to look like. So how does this work? If I take this vector and I multiply by a scalar phi, right? What I am saying is that what you end up is phi times dx in the I, phi times of, sorry, let's write it in the same form, right? You're just applying to this, applying this operators. That's what you're doing. Okay? So that's what this really means. Now, what if this was a vector, right? Now, when I have a vector, I cannot multiply a vector, but I can take a dot product of a vector. So let's suppose I have a velocity field, and I call this velocity field UI plus VJ plus WK. And then what if I take, let's do it two different ways. What happens if I take this dot delta, right? If I take this dot delta, note exactly what's going to happen. This side over here is you're taking the dot product of U, V, and W. And then on this side, you're taking the dot product of partial respect to X, partial respect to Y, partial respect to Z. So what's really going to happen here is so you're taking this dot product. The result of this is nothing else than the multiplication of this first times this. So this is what you end up with. Partial of X plus V times partial of Y plus W times partial of Z. And you can immediately see what's happening here, right? You can see that this is not on this side, it's actually on the before. So this is saying that any operator that you want to apply to this then will actually equal to that. Okay, for instance, let me explain this. Let's suppose I wanted to say, I'm going to write it right here, this dot this times phi. So because I apply phi, you take this whole thing and you apply phi to it. And applying phi to it is saying you're applying phi to all of this. So this is U partial of phi respect to X plus V partial of phi respect to Y plus W partial of phi respect to Z. Okay? So that's what this means. Now, if I do it the other way around, and if I said, now I'm going to take this, I'm going to take another dot product, let's see what happens then. So what happens if I say, I want to take this, and I want to take this dot product, but then once I take the dot product, I want to multiply this times my velocity vector v. Let's see what happens. So if I did that, then basically you're taking this expression right here. That's the first expression. So it says u partial of x plus v partial of y plus w partial of z. All of this, and I want to multiply v. So when I do this, then you basically end up with u partial of x times v plus v partial of y respect to v plus w partial of v respect to z. And note now that this term right here that I just derived for you is actually identically equal to this term that we have here, right? So in general, what we could do is we could say your acceleration vector will be nothing else than the derivative of v respect to t plus your velocity vector take dot with your gradient vector multiplied by v, and that's what this is going to equal to. The beauty of expressing it like this, now my delta operator can be anything. My delta operator could express it in terms of Cartesian coordinates, in terms of sorry, I can express it in terms of Cartesian coordinates. I can express that in terms of cylindrical coordinates. I could express that in spherical coordinate. For instance, your del operator in cylindrical coordinates is actually looks like this. Cylindrical coordinate, this operator will be ER partial of R plus E theta. Don't forget this 1 over R that's often skipped out and forgotten, plus EZ partial of Z. Okay? So you can see that this is more general and can apply to any type of problem, which is very, very convenient with the stuff that we do. Okay? So given this fact, we got another property that's very useful. Then what happens if I say V cross product of A, a vector A, let's say. Okay, so I'm taking the cross product now the other way around. If I did that, then what you happen is I have various solutions, right? If I'm working in now, let's say A, Cartesian coordinates, then you will end up with AX, X, AY, respect to Y, AZ, respect to Z. Okay? In cylindrical coordinates, you will end up with 1 over R partial of R AR divided by R plus 1 over R partial of theta respect to theta plus partial of AZ respect to Z. Okay? Now, if I want to do the cross product of this del operator, what we call this, we actually we have a name for this. We call this the divergence of A. Okay? Now, if you want to find the curl of A, this is very important, especially when we start doing rotational fluids. You take the cross product of this, then it becomes very interesting as well. When it's Cartesian, your Cartesian coordinates look like this. I, j, k, partial of x, partial of y, partial of z, ax, ay, az. These are the components of this vector. Okay? Now, if I did this in cylindrical coordinates, my cross product will look as follows. Take 1 over r outside this integral, outside the determinant, r times theta, don't forget it's r, ez, partial of r, partial of theta, partial of z, then you have ar, r times e theta, part r times az, sorry. Okay, so you got several cases depending on the coordinate system that we are actually working with. Okay, so it should be obvious that if you take the dot product of this, it will not be equal to 8a dot product of this. Also, if I take this cross product of a, will not be the same as taking a, the cross product of delta. Okay, those are two different properties and you get two different answers. Let's apply some of the concepts to some problems and see how this actually pans out.